Hello, welcome. Thank you very much for coming to our session today. We're kind of overwhelmed that so many people want to hear about collections, but very happy to know that because it's our enthusiasm as well. So, and we'd also like to say thank you very much to the organisers of DevOps for putting on this amazing event that we come to in some cases every year, in some cases only the once, but it's really amazing anyway. And we're very happy to be here. So today we're going to look at a number of topics in the general area of collections. We'll give you an agenda in a moment. First of all, we're just going to introduce ourselves for a moment. Stuart, are you going to introduce yourself?
All right, my name is Stuart Marks. I work on the OpenJDK at Oracle. I'm the project lead of the core libraries team. I'm also the maintainer of the Java Collections framework. I've done several collections-related JEPs, including the collections factory methods. There's deprecation, which I also do as Dr. Deprecator. That's not related to collections. But the two main collections JEPs I've done are the collection factory methods, which gave us list.of and set.of, the unmodifiable collections, and sequenced collections, which went into JDK 21. And I hope everybody here is upgrading to JDK 21 and later and enjoying the new collections interfaces.
Okay, that's you. So this is me. I wrote a book on Java generics and collections a very long time ago for Java 5, and then I wrote a book about Java 8, which was streams and lambdas, and I'm a member of various community programs, and I speak at conferences a bit, and I'm a Java rock star, which is what that thing at the bottom right is. And today I want to start off by promoting unconferences, which everybody should know about. This is a kind of movement, I would say, that is very popular in the Java world and elsewhere, but particularly in the Java world. And what an unconference is about is kind of the opposite of this. This is a very amazing event, but unconferences are the opposite in the sense that they're much smaller, and you don't have somebody at the front speaking to a lot of people in an audience, but they're much more communal. They're very equitable discussions, and we have a lot of technical discussions, very deep ones. It's a chance to meet experts in the field and talk to them on a one-to-one basis. And we also have some fun as well, as you can see from the pictures there. The pictures are all about fun, but there are very serious technical sessions as well. So I'd encourage you to learn about unconferences. The Unconference Alliance website is junconf.org, and it doesn't say very much at the moment, but that's because it has pointers to the various unconferences there are around the world, and we're going to put some more material on it explaining about unconferences. The one that I particularly want to advertise is JAlba, which I organise in Edinburgh every year in May, and it's going to be on the end of May next year, and you can go to the website, or you can when I revive it, because it's not working at the moment. And I would encourage you to consider coming to Edinburgh for 3 days of deep technical discussions and also great socializing as well, and getting to know a lot of people. So that's most of the introduction. Oh, sorry, I've got a little bit more to say. Sequels can be better. We are now on Escape from the Planet of the Collections. This is something that doesn't actually mean much to some people here, but the original idea was we're modelling it on Planet of the Apes, the Planet of the Apes series. I don't know why we're escaping from the Planet of the Collections now.
Escaping from old ideas.
Escaping from old ideas. So the book on generics and collections, which I wrote with Phil Wadler in 2006, is going to be updated, and I say this every year, but this year really, really is going to be updated to Java 21. The authorship still says Maurice, Naftalin, and Phil Wadler, but actually technical editor is Stuart Marks, who's kind of a joint author now as well. So I would encourage you to look out for that. That book is going to be appearing in the first quarter of 2025. And it really, really is this time, Stuart. No matter how cynical you are about me. This time for sure. So that's our introductions, the throat clearing stuff. And what we're going to talk about today, our agenda looks like this. We've got 3 main sections. We're talking about design issues. So around about collections and object orientation. It's how do we fit the ideas of object-oriented design in with collections. And you might think this is well-trodden territory, because people have been talking about this stuff for a long time, but it turns out that we do have something that's, if not totally original, that's definitely worth saying and not widely known. And then we'll look at a couple of design controversies in the collections framework. So we're going to talk about set membership, which often puzzles people, and we think we figured out something that's kind of relatively novel about that. And we'll also go back to the age-old question now of why it is, whether there should be immutable collection types, which is often said within the collection framework. And we'll look at ways in which that can be done and the problems about doing it. And then we've got a section at the end on the futures of the collection framework. Breaking the 32-bit barrier is about very big collections, bigger than int-sized, and a big change that's coming down the pike, which is Valhalla, for very long. So that's the agenda, and that doesn't map onto the physical agenda for the afternoon, which is going to be, we'll talk for about an hour and a quarter, and then we'll have about a half an hour's break for comfort and coffee and all that, and then we'll talk for another hour and a quarter, and then you really do get to escape from the planet of the collections. Okay, so heading off then, Part A, Item 1, establish and respect ownership of collections. You think you know about encapsulation, and you kind of do, but it turns out there may be a bit more to it than you thought. So oh, this is you, isn't it?
Yeah.
Okay. Okay. Right.
All right. Thank you. All right. So what are you using to advance here? I'll just use the arrow.
Yeah.
Okay. That works. Okay. So in object-oriented programming, most of you are probably familiar with the idea of encapsulation. You have an object and it has data in fields, and you want those fields to be private so that you don't have code outside mucking around directly with the fields. Instead, you provide access to them through methods, typically getters and setters, but also other methods will have, the methods on the object have exclusive access to those fields, so you don't allow direct field access. Now, in JDK 16, which is kind of, it's a couple years old, but it's fairly recent in the long history of Java, JDK 16 introduced record classes, which are really nice because if you have something that does not have very much behavior, but just has an aggregation of data, then you can put it into a record. And so this one line of code you see on the screen here, record rec string int integer, with the empty braces. That's a complete class. It's a different kind of class called a record class. And what this does is it tells the compiler, well, it's built into the language, but what the compiler, the language will provide for you is, it says, oh, okay, this record has two components, and this is a new concept. A record has components. It has a component named string, whose type is string, and a component named integer, whose type is int. And what it does for you is it creates private fields with those same names, and it also creates public accessor methods, or like getter methods. But they don't have get in the name. They just say string pren and integer pren. They're just named after the component name. And so what this does is it provides you a class oh, and then it also it provides you equals, hash code, and toString methods. So this, if you have an aggregate of data, this provides it provides a class that is a transparent aggregator of data. So this is pretty nice. It provides the getters for you, but the class is effectively immutable. You can't go in and, certainly clients can't go in and change these. These fields are final by default, so you can't change them. So this is really nice. You have a record class, and in one line you can define this class, and it encapsulates these fields for you. So that's pretty nice. Okay, so let's move on to an example, which is let's decide to have a class that contains a set of edges. So you have a graph that has nodes and edges. A node class, which we're going to represent as a record, contains a set of edges. So that's pretty nice because we just defined a record, and it provides a final field, and it encapsulates this field for you. And as I said before, it also provides hash code equals toString, a private field edges. It also provides a constructor for you that takes all of the things, and so that allows you to create a new instance with all of the component values. Okay, so this is pretty nice. So if we have a graph and we have a node class with the records, that encapsulates the edges for us, right?
It's exactly what we want, yeah.
You think?
Sure. Yeah.
Okay. All right. Well, it turns out that as nice as records are, they don't really cover this case very well. And the problem is that if you have a set, it might be mutable. And so let's have some sample code here where you have so you have a nice node class, and so suppose you have some code that starts off by creating a new hash set, and then taking that hash set and passing it to the node constructor. But then it still has a reference to the hash set, and so it goes in and modifies that. So now it's modifying an internal field of the record. That's not encapsulated, is it?
It really is. It really isn't. So, if there's mutable data inside of your object and somebody else has access to that mutable data, they may mutate it.
Yeah. So this isn't working. So the caller has a reference to the node it just created, but it also has a reference to the internals of the node. So there's something, so that's kind of wrong. And so also this idea is records are immutable, but we've just broken that because we just mutated it. Okay, so there's a problem there. So let's move on to the next problem. So we have, again, some sample code. So this code creates a new node and then just provides a new hash set to it as its argument. But then it calls the accessor method or the getter method. So it calls node.edges.clear. So it gets the set of edges out there and then it modifies it again. Okay, well...
So the idea is that a node should have control over its own data. An object should have control over its own data. And here's two different ways in which you lose control over your own data. If mutable data is passed into you and the reference to it is held from outside, then outside can alter it. And if you pass a reference to your mutable data to the outside via an accessor, a getter method, again, you can have your data mutated by somebody else.
Yeah. Okay. So this is clearly no good. Okay. So there's a third problem here, which is so we still have our node record, and we have some sample code that creates a new node called node 1, and it just passes a new hash set into it. And then the second line, we create another node 2, but we pass in the set of edges that we get out of node 1. And so what that does is it gets the reference to node 1 set and then passes it to the new node 2, which dutifully stores it in its field, which is what it does. And so this object diagram below, you have node 1 and node 2 point to the same hash set. And so that's kind of a problem because like we saw in the previous slides, you can go ahead and mutate that, and that will end up mutating both objects.
Yeah.
And so really, we just said we want encapsulation, we want to protect access to these things. But the fact is that you have a collection here. Using a record is nice for many things, but if you pass in a collection like this in a record, or if you have a record with a mutable collection component, then there are many ways that encapsulation can be broken. So we need to do something about that.
Absolutely. Yeah. This last problem is really a combination of the first two, I think. Mm-hmm. Yeah, but the first two are enough in themselves to make us worry.
Okay, so what should you do about this? All right. So first, it's the thing about a record is it's very attractive. You can define a new record on a single line, but you can only do that if every record component is immutable. And so the first example, which I showed you, cleverly used string and int, which are immutable, right? And then, of course, we broke that immediately because we changed one of the component types to be a set, and a set can be mutable, and so now we've lost encapsulation. So what it means is that you have to perform some extra work in order to restore encapsulation. And so the first thing is, in your node record, you have to provide a constructor, and so this is the shorthand this is the shorthand constructor for the record's canonical constructor, which is one that is responsible for initializing all the fields. And so what it does is it takes as a parameter that set of edges that the caller passed in, and what it does is it makes a copy of it. And so then it stores that into its own edges field. And so what that means is that this record now has exclusive ownership of the set that it just created. So that's one thing. So what that does is it solves a problem where if somebody creates a hash set and then passes it in and then holds on to a reference, remember that earlier example we had. So if the caller holds on to the reference to that hash set and tries to mutate it, well, we've made a copy of it, and so it's not mutating our internals anymore. So making a defensive copy is the right thing to do in this case. The second thing is, what happens if somebody calls the edges accessor method? Well, it's going to get a copy of our. It's going to get a reference to our internals. Okay, set.copyOf is nice in this regard because what it does is it provides you an unmodifiable set. And so if you hand out a reference to an unmodifiable set, then that's not really a big deal because sure, if you want to hand out a reference to it, they can read it, but since it's unmodifiable, they can't modify it. So anyway, so this is so this fixes the problem as long as you are willing to have a set that is unmodifiable stored in the record.
Yeah, I mean, I told you I was going to complain about this example,
okay.
and now I'm going to complain about this example because it's very good, right? But it's wrapping up at least two things in the same code. The really important thing about what to do when you get state passed into you that you're now going to make part of your own private state is to make sure you've copied it. You know, in this case, of course, set.copyOf does make a copy, but it also, in addition, does the copy that it makes is unmodifiable, which we'll go on to talk about more. And that isn't strictly necessary. And the reason why I objected to it was this is a great example, in particular if you're working with the collections framework. And of course, this is a talk about collections, so why wouldn't we work with the collections framework? But you might in general get mutable data passed into you for which you don't have this nice copy of method that creates that clones the data structure that's been passed in and also makes it unmodifiable. So you might have to, and you didn't like this, but I would say you might find that you have to write your own method for making a clone of the data that's passed in. And you could choose or not choose to make that copy unmodifiable. It'll be very useful for you later on if you make it unmodifiable, because then when you hand references to it out, then of course you can hand them out safely because they're unmodifiable. But what if you actually want to modify your own data? It's your data, so it might not suit you to do that.
Right. Okay. Yeah. So let's show a variation on that, which is suppose that the component type is set, but suppose you want the edges to be sorted, and so tree set gives you sorting, and so you want to store the you want the record's internals to be a tree set. Okay. So that's fine. But so that gives you the sorting property, but there's no unmodifiable version of tree set. And so now if you have the edges accessor method return a reference to that, we've bought back into that problem where the caller can get the reference to it and then start modifying it, which again, you've broken encapsulation. So here, what we do is we have to override the edges accessor method and then do something to protect ourselves. And so here we have an example of another useful utility in the collections framework, which is given some collection, you can put a wrapper around it that makes it unmodifiable, and then you hand somebody a wrapper. So you still have a reference to the original thing, so you can modify it if you want. But since you've wrapped it up in an unmodifiable wrapper and returned it to the caller does not have the ability to modify it. And so what I think Maurice was saying before, so this is nice because this illustrates in these two slides several things that the collections framework provides you. It gives you copying factories like set.copyOf. It gives you copy constructors like here, the new tree set that takes a collection. And then it also gives you unmodifiable wrappers. Yeah. And I think what your point was, if you create a record and one of the components can be mutable, then you don't necessarily have those things. And so if you put a mutable component into a record, you've lost encapsulation, and so you have to do something about that. And you might have to resort to making defensive copies. Many things do not have this idea of an unmodifiable wrapper. Like suppose you're using a string builder. That's a mutable object. I suppose you could create a string builder that has an unmodifiable wrapper for string. Actually, no, you can't, because I'm not sure. Is it a final class? But nobody does that, right? So there's something suspect about the idea of using a mutable component as a record, because it's really, you have to do this extra work to preserve encapsulation.
It's a problem. I mean, this is true. I mean, for records, it does look kind of odd, but you're going to get this problem with all kinds of classes as well.
Yeah.
I mean, we're focused on records because they're meant to be immutable, but actually the same message applies to all objects that own their own data, have to receive data for their initialization or for their modification, and have to hand out references to it. They're always going to have the same problem. If an object really wants to own its own data and have control over it, then it's going to have to take the measures that we're describing here.
Right. Okay. So let's
just say one more thing. Just say one more thing about that example. You'll see that the accessor there might have to do a lot of work or some work at least, every time you call it, because it's going to wrap an unmodifiable wrapper around the set. So that was the advantage of having the thing being unmodifiable in the first place. The way the copy of method was there. In this case, it might well not be very much work, but in other cases, it might be.
Yeah. Okay. So let's revisit one of the previous examples that I showed, where you create a new node, passing in a new freshly created hash set, and then create a second node by getting the hash set out of the first node and passing it to the second when constructing it. And so now, since we've added the copy constructor since we've added the copying constructor in the records constructor, and we've added the unmodifiable wrapper in the edges accessor method, then now the resulting object diagram is what we have here. So you have each node has its own instance of a tree set that it has exclusive access for, and up to, and that's what you want. You don't want any structural sharing between these things. Okay?
Yeah, absolutely.
All right. So let's summarize this section here. So our general policy is, and like you were saying, this does apply to records, but it applies to general classes as well. If somebody is passing you in a collection, and you want to store the elements of that collection, you need to make a defensive copy of it. Otherwise, the caller can retain a reference and modify things out from under you. The second thing is, if your object or record contains mutable components or fields or something like that, you need to make sure that you don't expose those to mutation in your getter methods or your accessor methods. So if you have an unmodifiable view, like you have in collections, then you should wrap it up in an unmodifiable view. Now, if your internals are not modifiable, then sure, just hand out a reference to it, because that doesn't create any danger of somebody modifying it, because it's unmodifiable. So if you've written your classes in this style, then what you gravitate towards is this idea that if you're mutating a collection, that you should only mutate collections that you've owned, and you know that it's safe to do so because you've made defensive copies of anything passed in, and you know that nobody else can do it. And to protect yourself, you can wrap things in an unmodifiable wrapper. But in general, if you're writing some code and you've gotten a collection from somewhere else that you don't own, then you probably shouldn't try to mutate it. One is because if the guy who gave you the collection is following these rules, you're going to get an exception because you're going to try to modify an unmodifiable collection. But if the developer of that code has forgotten to do that, you will probably end up mutating somebody else's internal state, which is a bug lying somewhere. Hence these items here only mutate collections that you own, that you know you have exclusive copies to, and don't mutate collections that you've gotten from somewhere else. And so there's this phenomenon which we're going to spend some time talking about later, which is that if you attempt to mutate a collection that is unmodifiable, then you will get the unsupported operation exception that various people have complained about from time to time.
From time to time.
But anyway, if you follow these rules, then you will avoid getting that exception.
Right. Okay.
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 True.
Right. Oh, by the way, something we didn't say, but I think we should say is that if you have any questions as we go along, I mean, obviously we'll make time for Q&A at the end, hopefully. But if you have any questions as we go along, please let us know about them, because
so I don't know if
it's a long talk.
That's true. I don't, but I think we'll have to figure out if you have a quick question, maybe shout it out, because I don't think we have mics, and then we'll have to repeat it for the recording.
Well, we'll repeat it for the recording.
Yeah.
No. We'll try to manage it, because we're talking for 3 hours. You don't want to save it up for all that time.
Right.
Okay. Right. So that's to my mind, this is about realizing the idea of encapsulation, which we know is a good thing in principle, but actually seeing what it means in practice on a kind of larger scale of it's kind of a software engineering question rather than specifically like what are we going to do about the much smaller scale issue about setters and getters. Okay, our second item is about custom collections. This is actually a kind of standard thing in object orientation, but it's particularly important for the collections framework, because the collections framework actually really thinks a bit about what it means to extend functionality of quite complex classes. So it's pretty common to want a collection that has that does most of the things that a standard collection from the platform library does, but has its behavior varies in some kind of minor way. And after all, that's what object orientation, that's what inheritance is supposed to do, isn't it? You're supposed to be able to inherit your methods and just modify their behavior slightly. So we've taken as an example here to show how you can and probably can't do this in the collections framework. The idea of a list with a single fixed element in it. So at the time that it's constructed, this fixed element goes into position 0, and from then on it's pinned to the front of the list, and it's never moved, replaced, or deleted. So it's a pretty simple idea, and it looks like quite a small modification to the behavior of list. So, because we know that inheritance gives us this feature where all we need to do is inherit from a class and alter the behavior of one or two methods to make sure that to get our different modified behavior. Let's do that. We're going to create a subclass of array list, and we're going to override methods in the array list until we get the behavior we want.
No BS. This really happened. So quick aside here. So a lot of some of the material in here is based on examples of real questions that people have asked, or also bugs that we've gotten. And so somebody said, "Here's what I did, and now my code is broken." So foreshadowing. Okay. So anyway, but this is something that sometimes people do. It's like, okay, well, array list is a great list. Everybody uses it. And so let's create a variation that pins the first element, and we'll just override the methods to prevent that first element from ever being moved.
It doesn't. I mean, if you've learned about inheritance in your classes on object orientation, it doesn't seem like such an unreasonable thing to do. Let's try and see what happens when we have a shot at doing it. All we need to do is just make an inventory of the methods that we need to change.
Right. Okay. All right. So we have an array list, and so just so it makes it a little easier, I've called the subclass fixed first list, and we've provided a constructor here. So E is the element type, so we'll keep it being a generic connection. And so we have a constructor that takes a single element E and initializes the list.
Okay.
And that's going to be our first element. Okay, so that makes sense. And so we have plenty of room here to override methods that we want to override.
In that box.
Yeah.
Okay. So obviously something that we can't do is put an element into the first position. So we need to think about the methods that might put an element into the first position.
Right.
Because we're going to throw a legal argument exception or something like that if you try and do that.
Yeah. Okay.
So add can do that, can't it? The add can take an index that says
Right.
I want to put an element in there. So let's put that one in.
Yeah. Okay. So yeah, we're gonna have to override that and put some logic in.
Right. Yeah. Now, if you have to change the behavior of add, you have to change the behavior of add all, because that adds an entire collection, and we need to. But again, it specifies the index at which it's going to be added. And we need to make sure that it's not added at index 0. So we've had to put that in.
Well, doesn't add all just call add? I mean, if you're doing add all in a collection, doesn't it just call add on every element of the collection?
I don't know, because I haven't looked at the code for array list.
Okay, you
does
didn't?
it? Yeah.
Well, I did, and in fact, it doesn't call add.
Oddly enough,
but this is already there's an issue coming out here, because sometimes, in fact, there might have been a past version of array list where add all just called add, and so you might think if you're doing this, you just need to override the add method. And then, okay. Yeah. So, but yeah, okay. So this is a little odd. It's like, it's not obvious why you overrode add already. Why do you also have to override add all?
Well, of course, it depends how it's implemented.
Yeah.
Because it might be implemented on top of add, and there might be a more efficient way of doing it.
Yeah.
So we better go and have a look at the code. Do we see a problem here, possibly?
Yeah.
Okay. Anyway, let's carry on. We can't remove it. So what are the things that might remove that first element? Well, we could actually remove. There's a method that removes all of the elements. So we better override that to make sure that it removes all of them except the one at position 0.
So that should clear everything except the first element.
Right.
Okay, that's pretty easy.
Okay, right.
Okay.
So I think we'll have to worry about that. Oh, right. So whoa. So what do you want to say about the next things?
Okay. Well, so the general interface for accessing elements of a collection is iterator, and list not only has an iterator method, it also exposes a couple list iterator methods. So why don't you go ahead and show that
But
now.
why do we have to put those in there? All they're doing is just iterating.
Yeah, if you just iterate over
they're just iterating along the list, right?
Never forget, iterator has a remove method.
Oh, shit.
And so if you say list.iterator.net, you have to store it. Basically, you can call next on it to get the first element, and then you can call remove, and it actually removes the element. It just returns you. Yeah, it's always one of those things. Iterators, you think, that it's just kind of weird having remove on an iterator. So yeah, you have to override the iterator method here and do something different.
Okay. Well, we're done now, aren't we?
Well, so list iterator is another kettle of fish.
Oh, of course, you can go backwards with the list iterator.
Yeah, so list iterator is kind of interesting because you can move backwards and forwards. And not only can you remove, so list iterator is a sub-interface of iterator. And so iterator you can move only forwards. In list iterator you can move forwards and backwards in the list. And not only can you remove, you can also add and set elements. And so you can position the list iterator and add something at the front or set the first element to something different, which violates. So yeah, we have to do some more work here. And our class is full already. What are we going to do?
Yeah, I'm not sure. I mean, there's still things that we haven't thought of.
Yeah. So
I'll tell you what. Let's extend it a bit.
Okay, good. All right. So solve that problem. All right. There's some things.
There's some things we can solve.
All right. So that's dodged a bullet there.
I've obviously thought since there's a remove method on iterator, there's also a remove method on list, so we're going to need that. But there's two remove methods on list, because one of them removes at an index, but the other one actually finds a match for the object you want to remove and removes that, and that might be the first fixed element. So we better put that in as well. Okay. And there are various other methods of remove things, aren't there?
There are. There's a whole other family of remove methods.
This isn't looking good, is it?
No.
All right, here we go.
So remove all, but again, don't remove all, and so retain all is a little strange, but it's a complement. But retain all actually ends up removing the elements that you're asking not to retain. So retain all is a removal method. So these all end up removing things, and so we'll have to override those to make sure that they don't run into the circumstances where they might end up removing that fixed first element. So But and again, they aren't necessarily implemented in terms of the other remove methods.
We don't know the implementation, so we'd better be.
Yeah, and actually, I went and looked at the code. It's pretty hairy. So
is that
yeah, it just doesn't remove doesn't call the remove int method. No, they do a lot of complicated stuff.
Yeah, they.
Yeah,
those people at Oracle.
Yeah.
Yeah, okay, well, we're done now, aren't we?
Okay, well, we're out of space again. All right,
all right, here we go.
Come on. Okay.
Right. What we haven't got yet, the very simple thing is you can change an unmodifiable list at the index you specify. So we better have that.
Okay. That one, I think, is pretty easy.
Yeah,
we just check to make sure that the index is not 0. Okay, so we're almost done, right?
Right.
Okay.
Sublist. Sublist. Why do we have to override sublist, Stuart?
Well, okay. So sublist is a complicated beast. So what sublist does is it provides a range of a list based on index, but it returns a view onto the underlying list. And if you mutate the sublist if you say sublist, well, you give it 2 indexes, from and to. So if you say sublist from and to, and then you mutate the sublist itself, those mutations push down into the underlying list. And so if your subrange that you created with sublist includes that 0th element, then modifying the sublist could also end up modifying the underlying list, which could break our invariance again. And the thing is, sublist, the return value of sublist is a list, which means that I think we have to override all of these methods in the sublist implementation as well.
It's really not looking that good.
Oh, that's a lot of.
Yeah, I think we're dragging this out a bit.
Yeah,
honestly.
Okay.
We're not finished.
Yeah.
I mean, it's true we've reached the bottom of the slide. So actually, what we had
so
to
we
do
better
was
be finished because
we had to go off to one side.
We better be finished because there's no more room.
There's room on the right-hand side.
Yeah.
These methods, iterator, list iterator, and sublist, all of them work by, they all have pretty complicated inner classes that implement their behavior. And those will have to have their behavior changed.
Right. So if you go look in the actual array list implementation code, there are nested classes inside of array list for iterator, list iterator, and sublist. And actually, they are non-trivial. And in fact, sublist really is a complete list implementation that essentially has implementations that do some checking and offsetting and whatnot, and then delegate to the underlying list. And so they don't necessarily go through the public interface for lists. Since array list sublist is a nested class, it has direct access to array list's internals. So we really do need, if we were pursuing this approach, which I'm hoping you can see is starting to realize that this idea of just overriding stuff until you get the behavior you want is kind of a bad idea.
Yeah.
And because you're buying into, in order to provide all those invariants you want, you're buying into overriding and rewriting a lot of code.
And here's the clincher.
Yeah. Okay.
Here is the clincher. You think all of this was bad enough, but supposing you managed to get it all worked out.
Yeah. So we wrote all this code, tested it, works perfectly on JDK 17.
Yeah. Right.
Okay. Have you guys been reading ahead? Yeah.
So you're going to have to maintain this code, and it's worse. It's worse than even what that thing at the top right suggests. New methods got added in, and you're going to have to to look at all of those. But also, the behavior of some of the existing methods may change, so they start to depend on internal calls, and so you're going to have to check over everything that you've done and possibly alter everything that you've done because it might not work anymore.
Yeah, so as you can see here, so in JDK 21, we added sequenced collections, which added several new methods, including these new methods on list. And the ones I've marked with a plus here, add first and remove first, can clearly impact the fixed first element. So the problem is, if you've done this approach where you want to override all the things that you need to override, the next JDK release might come out and add some new functionality that allows callers to bypass the invariants you carefully tried to set up by doing all that overriding. So once again, this can just bypass all those overrides you did.
You missed a plus sign there. What about remove last?
Oh, that's right. Actually, that's good.
Yeah.
Good point. We have to debug our slides too. You know, there are bugs and everything. Yeah. So if there's one element in the list, remove last will
And what would add last do to an empty list? Oh no, we don't have an empty list. No.
That's right. Yeah.
Right, okay, I think you get the idea. It's not going to work. So a list it's a rich API, but you often get this problem with. I mean, we've just taken this as an example, but most real-life classes maybe don't have thousands of lines of code in them like ArrayList has, but they may have a lot of code, and the collections are particularly complicated. So you get these view collections as well, things like sublists. Sublists is particularly strange because of all the views that you get in the collections framework, ways of seeing a collection as though it were a different one, like, for example, looking at the key set, the set of the keys of a map. Sublist is unusual in that it is completely transparent. It's the only one, I think, that is completely transparent. Any change you make to a sublist will map through to the underlying list. And so obviously, if you want to change the behavior, you've got a lot to do. Iterators with side effects are a source of unpleasant surprises, and the fragile base class problem. Okay, so I think we probably don't need to go on too much about this. I think we've kind of made the point. Last year, I think we actually started off coding this. Yeah. That was not a good idea.
Yeah. So just a quick summary of the fragile base class problem. So I think there are really two things we illustrated here. One was this issue that I mentioned early on. It's like a lot of implementations of object, a lot of implementations use their own public interface, and therefore you can modify the behavior by overriding a public interface. And so if add-all were implemented in terms of add, then all you need to do is override add. But what you've done is you've introduced a dependency on how your superclass happens to be implemented today. And if it were to change tomorrow, then your code might break. So that's one issue. And then the other issue is the potential addition of new methods in the next release of the system. Then that can also have the effect of breaking your program. So there are probably a few other ways that changes to superclass can break subclasses. So that's the general issue here, that when you take an approach of modifying behavior by subclassing, it actually is pretty easy to get yourself into trouble. Now, if you control both the superclass and the subclass, then yeah, you can maintain them in tandem. But if you're subclassing somebody else's implementation, it is very, very easy to accidentally create these dependencies that can get you into trouble down the road.
Now, the original author of the Java Collections Framework was Josh Bloch, whose book, Effective Java, wags a finger at you in a fairly forceful way about this and says, if you expect a class to be subclassed, you should design it for inheritance. And true to his word, that's exactly what he did in the collections framework. So a better approach than all this that we've been talking about, which we've taken a long time to explain, really doesn't work, is instead to create a subclass of abstract lists. So there's an abstract list, abstract set, abstract map, and that's it. I think. Yeah.
Abstract collection.
Abstract collection. Yeah. So, and these are Josh being true to his word. They are designed for inheritance, and if you want to implement a list, say on inheriting from abstract list, all you have to do is to extend the class and provide implementations for the get override that takes an index and the size methods. That's all. If you want it to be modifiable, then you've got to do a little bit more. You've got to override the set method that takes an index, which is the only one, and the add method that takes an index, and the remove method that takes an index. Only those 5, and you can get the behavior that you want.
Yeah. So this is so these paragraphs here are a quotation from the abstract list specification. And so this is as opposed to ArrayList, which has nothing of the sort. Abstract list says please subclass and override these methods in order to get the behavior you want. So abstract list is tailored toward the subclass and override to customize behavior.
Yeah, right. So your better approach just looks like this. Only five methods to be overridden. It can depend on an array list, but it depends on it in a very controlled way. So last year I tried to code it, but you don't want to watch the video of that. So this year we've just used the code that we developed last year in the session, as it happens. Let's see if I can bring it up. So there we go. And this is what it looks like, and it really is remarkably simple. Just those 5 methods is all that we wanted. So the constructor for list with fixed first element from abstract list. The constructor takes a single fixed element and it puts it into a backing list. So we're depending on the behavior of array list, but we're going to use it in a controlled way because
right.
we're in charge of what's going on. So we add the fixed element in there, and then if somebody tries to set, if a client tries to change the value of an element at a particular index, we just check whether the index is 0, and if it is, we don't allow that. We throw an illegal argument exception, and if it is, well, we just pass that through to the backing list. If somebody tries to add an element at a particular index, we make the same judgment. We just check to see, is the index 0, and if it is, or if it isn't, then we pass that through to the backing list. Otherwise, again, we throw an illegal argument exception. So these are really simple. I mean, this is amazingly straightforward compared to what we were thinking about before. It's kind of magical, I think.
Yeah, and that's it, right? There's get. Oh, and what's the last one? Size.
So remove obviously won't allow it from the first element. Get just passes it through to the abstract list, and size simply delegates to the backing list again. I mean, literally, even I, and I'm kind of known for my competence at the keyboard in talks. Even I would actually manage to code this in the talk last year. So that tells you how easy it is.
All right. So is that it for this class?
That's
okay. So you have a test method
We've got some tests, but we won't run the test because it actually works.
Yeah.
I mean, amazing.
You'll have to trust us on that.
Yeah. Oh, yeah. Trust us. You would do that, wouldn't you? So that's a really quite a powerful demonstration. I mean, maybe slightly contrived, but not very contrived, of just how much better that approach is than the idea.
So before you move on, I wanted to mention something. So you saw this in the code, but there's a common technique here, which is to in your subclass you don't have to maintain all of the data structures yourself. What you can often you could if you wanted, but what you can often do is just use one of the existing collections, but keep it encapsulated, and then you can let that data structure do the heavy lifting for you. And so you saw the code was pretty simple.
Yeah. Okay, so we've got a conclusion from this. Abstract list, abstract set, and abstract map are meant to be subclassed. They're designed for it. So you will not get any of these unpleasant surprises that we talked about with the fragile base class problem with them. All the method implementations funnel into these 5 that we overrode there. They delegate actual storage to a private collection, and in general, this is something that we are hearing from a kind of reversal from the early days of the doctrine of object orientation. Prefer delegation to inheritance. It, generally speaking, ends up with much simpler and less closely coupled code. Only problem: it may not be very efficient. So these implementations in the abstract collections clearly aren't optimized. They can't be because they're designed for very general use. Sorry, and so it may well be that you're going to have to add extra custom methods that will improve performance. But you can start off with this as a basis, and you can be confident that it'll work.
Right. Yeah, and so what happened to all that sublist implementation? Well, abstract list has its sublist implementation, and it handles all of the stuff for you, but then everything boils down to add of index or set of index or remove of index or something like that. And so you get all of that stuff if you subclass abstract list. Okay.
Cool. Okay, how are we doing for time? 40. What did
All
we
right.
say? What was, okay, we're good.
Yeah.
Okay, right. Right.
Okay.
Questions? No. Yeah.
Yeah, you go ahead. Sorry.
When we were using this backing list in our
I'm sorry. We're taking a question in the front. We'll get to you in a moment. Yeah.
if instead of operating on the backing list directly and checking if we're operating on the first element or not, if we were operating on a sublist of the backing list, where the sublist would go from the second element on, so we could get everything directly on the view of the backing list that would go from the second element on.
Okay. How do we summarize this question?
So the question is, if we were working on a sublist, then we might think that the sublist, the zeroth element of the sublist, if it was fixed, mapped onto a non-zeroth element of the backing list, and it's the backing list whose zeroth element we want to preserve. Did I get that right?
Yeah, I
Did I
think
get that right?
so.
Yeah, sort of. I'm getting half a nod.
Yeah, but and I think one of the things you do have to think about this a little bit, because sometimes when you wrap a collection and delegate it, sometimes it's tempting to say, oh, all I can do is I can just delegate sublist to my internal delegate. But that actually is potentially dangerous, because sublist is so powerful that if you let the backing list sublist leak, then that might be able to break your invariance. So in fact, abstract lists sublist implementation really does funnel everything down into like add of index, set of index, and whatnot. So if you have guarded those methods properly, which I think we showed in the code, then even the sublist stuff will all continue to remain protected.
I was not talking about
Oh.
the sublist implementation that we let leak out. I was talking about the internal methods that were always operating on our backing list. And they were always checking if we were operating on the first element or not the first element.
Mm-hmm.
If those internal private behavior was operating on a sublist of this backing list, this is my point. So if I was adding something at the beginning, I would be adding at the beginning of the sublist of the backing list, which means I would be adding on the second element of my real backing list, and so on. If I was removing my backing list, I would be removing the sublist view of my backing list, which means that I would still retain my first element and the rest of the list will disappear. If I would add something.
Yeah, I'm not sure I understand the question. Maybe we can talk about it afterwards. I'm sorry. Okay. So there was a question farther in the back.
I suppose the current implementation of array list is not an abstraction of subclass of abstract list, but will it be possible in the next version of the JDK to implement the array list as a subclass of abstract list?
Array list is a subclass of abstract list. Yeah, it extends the concrete data structures all extend the abstract data structures already.
So actually, that's an interesting point, though, because array list effectively overrides everything so it doesn't actually inherit anything from abstract list.
No.
And so actually, that's a little bit of its implementation leaking through. Mm. And so unfortunately, it's not compatible to remove a subclass, even if it won't have any functional effect. So. Okay.
Okay. Right.
I think we should move on here.
Okay.
All right. So let's see. So this is mine then?
This is yours.
Yes.
Yeah,
okay.
We're going to talk about composite keys.
All right. So let's start with an example here. So suppose this example is pretty close to home. Suppose we have a bunch of books.
A bunch of books would be nice. A single book would be kind of nice.
So let's cook up a book class and put some fields into it. So we have a title, we have the author, a publisher, a page count, and so forth. And now this will be a conventional class, so that means we have to write our own, all our own stuff. Okay, so presumably we would have some getters here for getting the fields, but then we also have to write our equals method. And so it's a typical, there's nothing really going on here. But it's a typical thing where we check reference equality, we make sure the other object we're passed is an instance of book, and if it's not an instance of book, we always return false. But if it is an instance of book, we just go ahead and compare all the fields. So the title, author, publisher, and page count all have to be equal in order for two books to be considered equal. Okay. pretty straightforward. And then we have a hash code that hashes all of those fields together and provides us the hash code for a book. Okay, so that's pretty straightforward. There's really nothing unusual going on here. All right, so now that we have our book class, let's start to work on some simple tasks here. So let's say that we have a bunch of books, and we want to see if, given a title and author, whether we have that book in stock. Okay, so what kind of questions would we want to talk about the design here? So first of all, we want to say what collection should we store this in? Because you have a bunch of books, you want to store them in a collection somehow. And then okay, so if we're asking a question, that's going to involve some searching. So do you have this book? Okay, so we're going to have to think about searching that collection, and so what algorithm are we going to use for searching? Okay, so let's move on with a pretty simple example. I think simplest data structure is a list. So we have our library that has a bunch of books in it, and we put it in a list of books. Okay? And now we have this hasBook method that takes a string and, takes two strings, a title and an author. And so pretty simple. We just do a for loop over it, and we're just looking for a book whose title matches and whose author matches. And if we find one, we return true, otherwise we return false. So again, this very simple example just to set up the problem. Okay, now since we long ago upgraded to JDK 8, we can also use streams. And so we could, instead of a for loop, we could just use a stream and use this any-match operation on the stream. But notice the predicate for any-match is essentially the same as it was in the if statement in the previous slide. We just check the title and the author, and if they're equal, then that satisfies any match. Yeah. Is there something you were going to say about that?
No, not at all.
Okay.
Not at all.
Okay, so
it's perfect.
So anyway, all right, so this, okay, very simple, but of course if you have a lot of books, then you don't want to, I mean, basically the way you search a list is linearly. You have to run through everyone and then call all these methods for every element in the list. And linear searching is slow. The more books you have, the slower it's going to get. So we have all these nice other data structures in there, like hashset, for instance. And so the nice thing about a hashset is, okay, so you want to see if you have a book, and so if you translate that into collections API, then that turns into the contains method. And the nice thing about the contains method on a hashset is that it's order constant. You can add a whole bunch of books into your hashset, and with the proviso that your hash code is suitably distributed, such and so forth. You can, the runtime of your contains method is not going to be affected by adding more and more and more books because it's order constant. So that would be a nice thing to do. It would be really desirable, yeah. since especially if you're a big book publishing house, you might have thousands and thousands of books. Okay, so let's redesign our library around a hash set. So our library is now a set of books instead of a list. We create a hash set and add all the books to it. And then now let's go to write our hasBook method. So we take a title and an author, and then, okay, so now we're kind of stuck because we have a set of books, but we have a title and an author. So how do we search a set? We can't do contains because there's nothing that takes two strings. Right.
Contains works on equality. You'd have to take the entire book and compare your book, the one you're looking for, to every book in well, not necessarily to every book in the collection, but you'd have to compare every field.
Yeah. So we could easily check to see whether a set contains a book if we have the book already.
Yeah.
But we don't have the book. All we have is the title and the author, right? Yeah. And so so this is not working. So we have to do something else. So so what should we do? So when we started off, we said, okay, so you have a book and a typical class, the equals and hash code compare all the fields. Okay. So we could say, well, since we're going to be searching by title and author, let's modify our class so that it doesn't compare all the fields anymore. So since we're going to be searching by title and author, just change the equals method so it looks only at the title and author, and change the hash code so that it only hashes title and author.
And I have seen people go down this road.
Yeah.
I won't say who they were, but it might have been me.
Yeah. Okay. So, you can see in the slide here that our editorial, we've inserted an editorial comment here. You could modify your class design, or you could contort your class design for the kind of searching you want to do over the collection that contains the object. So, okay. So the fact is that this you can get this to work. So let's see how we would do this. Okay. So we want to search for. We have a set of books, and we want to search for a book. We want to see if the set contains a book matching the title and author. But since we can only ask the set whether it contains a book, then we need to add a new constructor for a book that takes only the title and author.
Right. Okay.
Okay. And it just ignores the other fields.
Yeah.
Okay.
Seemed all right to me.
All right. So this. Okay.
At the time.
Yeah. So you can get this to work, right? So we have our library has a hash set in it, and the has book method takes the string and the author, and we create a new. Sorry, the title and the author. We create a new book from the title and the author, and then call the contains method on it, and that'll work. Okay. So. There's something weird going on here, though. I mean, if we're kind of giving each other the side eye here, it's like, did you really do that? Is this really a good idea? Yeah. And so what's going on here is your library has real books in it because they have all the. I mean, if you're a book publisher, you might your book object might have a bunch of other fields as well. We only had 4. But you can imagine it has lots and lots of other information in it. But if we're searching for just title and author, we had to construct a new book object containing only the title and the author. And so I've called that kind of a fake object here, because it's not a real book, right? It has no ISBN in it. It doesn't have the page count information. It doesn't have the number of copies in stock or whatever. It doesn't have anything like that. So. So let's see, I don't know why we had that one there. So a couple things going on here. So, this is the same code, but if you look at it closely, then we've created this facility for creating fake book instances, and our library has real book instances. And you can't see this by looking at the code. And so if you have a bunch of code flying around, then some of the book instances are fake and some of the book instances are real. And that smells to me like a situation that's ripe for having bugs in it. Okay. So I think we covered this already. Yeah, so if you want to call contains on a set, you already have to have an object that equals an object in the set. And we made that work by adjusting or contorting the object design of our book in that it only considers books equal if their title and author are equal. Then we added a constructor to do that. So we had to change our API for the book. And then now we have a system where we have fake books and real books flying around in our application. And so you can construct a system this way, and people probably have, but you can already see it's starting to get pretty uncomfortable. And maybe a set turns out to be the wrong abstraction, because we started off by saying we have a title and an author, and maybe we want to do some look. We have a title and an author when we want to look up a book.
We want to look it up. Yeah.
So
yeah, it's kind of obvious.
Yeah.
Yeah.
Well, it's kind of obvious, but the reason it's kind of obvious, but it kind of isn't. And the reason people don't do this is because they think, oh, okay, well, I can look up a book by author, so that's a map, or I can look up a book by title, and that's a map. But I want to look it up by title and author, and so I can't have a map with 2 keys. So that's
where the fake object comes from.
That's why people go into this. I can't use a map, so I have to use this fake object approach, right? So that's why people get trapped in this kind of thinking. Okay, but our claim is you can use a map, and in fact, you should. Oh, okay. So actually, so first of all, we'll just take a baby step forward, and we're saying, okay, so we're going to make this a little bit better. Oh, sorry about this. There was. Did I?
No, you're okay. No, you're okay.
No. Oh, go ahead.
No, you've moved on from having a set of looking at things with a set of fake books to looking at things with a map from fake books to real books.
Right.
And that looks like it's more sensible.
Yeah, and actually the other thing I forgot to mention from the previous slide was a set is also limited in that you can. So we were able to write has book. So do you have this book? Okay, so we create a fake book by title and author and say you have this book. Yes. Okay, give me the book. You can't, right? I have the fake book and I know the set contains it, but I can't get the one out of the set that's the real book that I want. And so set is really not the right thing. So that's what leads us to.
And we have another problem with sets. Supposing we've got different editions of this book, things that have unequal fields, but they're not unequal on the fields that are contained in the fake book. Because if equality is only being measured on title and author, then you could have a book with the same title, and you have two different books, same title and author, but different editions, and you've ruled that out. So that's pretty limiting. You really have contorted your object model quite a long way.
Right. Okay. So we've converted our set to a map, but it's a map from book to book, which there's still something a little odd about. We have our hasBook method, and so to have a book, you can ask the map whether it contains this key. Okay. So that will work, and then now we can write getBook, which we couldn't do at all with set. So if you want to look up a book by title and author, you can get the book, and the book that's returned is the real book. Okay, so that works so far as it goes, but we return to this idea of this notion of real and fake books floating around in your application, and I would say we said it before. We contorted our object design, and we have real and fake books. I think you said this already, right? So right now we are limited to looking up by title and author. And so if you wanted to look up by something else, you're toast because you've tailored your object to that specific kind of lookup.
Yeah.
Okay, so what's the solution to this? So the idea is to create this notion of a composite key. And so here are our friend records again. So if we want to look up something by title and author, let's just create a composite key called, we'll call it title author. Maybe you could call it something else. And so that first line there is our single line declaration of record. And this in fact, this actually works pretty well. You just have two strings and you don't need to override anything else in it like we did on the previous one, because previous example, because nothing is mutable. Okay. So now, and the point is we use our title author record as the key instead of fake books. So then we can clear out this notion of fake books and real books. And so we have book objects, and they're real book objects. And then if we want to do some looking up by them, we create these title author records. And we put those into a hash map, and the map is keyed by title author, and the values are book. And then so getBook creates a new title author record from the two strings, and then looks up in the map and gets the book and returns it. Okay. Was there? Oh, okay. Oh, yeah. Okay, sorry. All right. So that was basically. Did you want to go over these, or do you want me to continue? Okay. All right. So we went through a number of unsatisfactory options here, right? So we started off with a linear search. Okay, that's too slow. So looking in a set is really useful because it gets order. We have an order constant contains check, but aside from all the other issues, we can't retrieve objects from a set. And so when you're in a situation like that, you want to create a map, but now the question is, what should your key be? And you can have this notion of a fake book and a real book. But really, what I think the best solution is to have a key. The thing that's nice about records is it's very easy to create a dedicated class to use as a key. And I think the reason that people didn't do this a few years ago was that Java didn't have records. And so if you're doing this, you might be tempted to take shortcuts, or you might be tempted to contort your object design around this, because do I really want to create a new book key class and write out all the constructor and the toString and the hash? And so record does that for you. So it's much easier to create a composite key like this. Okay, so you create a composite key using a record, and then use a map from that key to the book. And we can avoid using fake books at all. Okay, and then so the other thing is that there's something about when you're designing an object, if you ever have a situation where equals and hash code don't cover every field of the object, you need to ask some subtle questions about that. The rule is that equals and hash code have to cover the significant parts of the object. And so if you have a field that, for instance, is a cache of data that you've gotten from somewhere, maybe that's not significant to the object because it does not change the semantics. But when you do something like this, well, a book has all this information, but for some reasons we're gonna use equals only on a subset of it. You have to think hard about why you're doing that. And so now we can restore book to its full status of having equals compare every field. But then the way we get this subsetting notion is by extracting those fields into a composite key, which is a different class, which again satisfies this notion of equality in hash code covering all of the fields of that class. And this is the class is our new our title author key. And then I think most importantly is we've separated out this composite key from the class itself. So if we did want to have a situation where we want to look up by ISBN or something like that, we can create a different hash map that's keyed by a different record that's used as the key. It might be a composite key or it might be something else. But then now you can have a bunch of different data structures that all have the same books in them but are indexed by something else. And so that's something you couldn't do before when you modified the book itself to do its equals and hash code only on the subset of things. Okay, so there's a design question remaining, which is what your book looks like when in the presence of this composite key. Do you actually store the composite key in the book, or there are a couple alternatives here? Thank you. So you could store the composite key directly in the object, or another possibility is to have a method on the object that constructs the composite key from the fields that are in the book itself. So there are a couple different ways to do this. It kind of depends on where you want to get the how closely associated the composite key is with the book. Or is it more closely associated with the code that's doing the queries? So it kind of depends on what you want to do. Okay, and I think that's it for that one. All right, do we have time for questions? We are
right on time for the break, I think.
Yeah, is it? You think so?
Well, it's,
that's true. Yeah, we're 1 hour quarters in.
Absolutely, to the minute.
Yeah,
pretty much. Yeah.
Okay, so half an hour break.
Yeah, half an hour.
Okay.
Yeah. Comfort, coffee, those kinds of things.
Okay, so it is 2:45 now. Return at 3:15.
Yep. See you back now.
Okay. Thank you.
Okay, we're back on.
All right, welcome back.
Yeah.
And
thank you for coming back.
Thank you for coming back, yes.
And we're not in the least bit surprised that so many people did. So in this second part, we're now going to talk a little bit about two controversies in the design of the Java collections framework. Things that trip people up. Well, one of them that trips people up quite a lot, the set membership, and one that they want to trip us up with, which is about immutable collection types. So first of all, let's talk about set membership. There's kind of some surprising properties of different sorts of sets. You think you know about hashset because everybody uses that all the time. But in teaching people, I've frequently come across people saying, well, like this is this weird thing with when I use tree set that it's got some nice properties, but elements keep on disappearing. Why is that? So let's have a look at that. we're starting off with a little demonstration, if I can manage to make this thing work, of some of the strange things that happen with sets.
Oh,
There
can
we
you?
go.
How is
That's.
actually? I think it would be good if you can. Can you make that bigger?
Can I make
or-
that bigger? Possibly can. Let's see. Does that work? Okay, that's getting bigger.
Yeah. Okay, that's probably good.
Okay, right.
All right. So why don't you start that off?
Okay, so I will
Let's,
start this off. So we're
run J-
running a JShell script.
Okay. And actually, before we get into this too much, so we're going to talk about set membership. Everything we talk about applies to the keys of a map as well.
Yeah.
So
Yeah.
I think maps end up being used a lot more than sets, and so all of this stuff is operative with keys of a map.
Right.
Okay, so let's see.
Tell me about the
So we want
setup.
to do the space bar here. Okay,
Yeah.
so all right, so we're creating a few sets here. So the first thing we're doing is we're doing something a little bit strange here, which is we're creating an identity hash map. So there's no such thing as an identity hash set. And so instead what we do is we create an identity hash map, and then there's a utility called new set from map that creates a set and stores the elements of a set as keys of a map. Okay, so that's what ID set is. And then hash set is just a new hash set of string, and then tree set is a tree set with a string with case insensitive order. Okay.
Yeah, just say briefly what case insensitive order is.
Yeah, okay. So a tree set is sorted, and it's sorted by the values of its members. And so string, if you just create a new tree set of string, then you throw a bunch of strings in, it does a lexicographical ordering based on string's compare to method, because string is comparable. And so what we're doing here is tree set has another constructor where you pass in a comparator, which is used to order the elements in the set, and crucially also determine which members make it into the set and which do not, and we'll discuss that later. And so string.case insensitive order is a comparator that's part of the standard library that does a string comparison in a case insensitive fashion. Sometimes it's useful to store things and look them up by case if you're doing case insensitivity. So this is a useful thing to have.
Okay.
All right, so we're going to be using three sets here: ID set, hash set, and tree set. Okay. All right, what happens next? Okay, so we're going to do something slightly odd here. We are going to take a char array that contains the lowercase a, create a new string out of it, and add that to the ID set. We're going to do that a second time, and then we're going to take a slightly different character array with a capital A, create a string from it, and add it to the ID set, and then we do the same thing again. And so the result is we have an ID set that contains, well, this is a weird set. It looks like it contains duplicates.
Don't say
Don't
that.
explain that.
Don't say that word.
Okay, all right. Yeah, that's okay. We're getting ahead of ourselves here. So the ID set contains 4 elements: a capital A, a lowercase a, another capital A, and another lowercase a. Okay, so now we take a hash set and add all of the elements from the ID set to it. So the hash set only has 2 elements. Okay, that's right. Lowercase a and a capital A. Now we're going to take the tree set and add all of the elements of the hash set to it. And now the tree set contains only the uppercase one.
They get smaller and smaller.
Yeah, curiouser and curiouser. Okay, so now okay, that's a little strange. All right, so we ask the ID set whether it contains a capital A, and if you look up on the screen, the ID set does contain a capital A. So why does contains return false? That's very strange. Now we're going to ask if the tree set contains lowercase a, and it says yes. Well, you can kind of tell there's something about case insensitivity. This sort of makes sense. Okay, now we're going to add a B to the tree set. So the tree set contains capital A, lowercase b. And now we're going to ask the tree set if it equals the hash set. And so if you look towards the top of the screen, the hash set contains a capital A and a lowercase a, and the tree set contains a capital A and a lowercase b. But tree set says they're equal. Oh, that's very strange.
I think that'll do us.
Okay, so now let's ask
No. All right.
let's ask the hash set if it equals the tree set. The hash set's smarter. It says no, I'm not equal to that guy. So anyway, yeah. So there's a lot going on under the covers here.
That's us.
goodbye. All right. Okay, have fun, everybody. Figure that. Come back next year and we'll tell you. No, no. Maurice is going to explain it right now.
Well,
and I will.
Yeah. Let's have a look. What is a set? I mean, after all, I mean, when you think of a set, what do you think it is? It's not ordered, of course, and it contains no duplicate elements. This is why I wanted to stop him saying the word duplicate. What exactly is a duplicate element? Well, if you look at the set contract, the specification of the set interface in the Java doc says, more formally, sets contain no pair of elements E1 and E2 such that E1 equals E2. Right? E1 equals E2. And this is in fact true for hashset, linked hashset, enum set, and lots of sets that we expect to use, and the corresponding maps, all the standard maps. This is true. But you've just seen that those are not that's not an adequate definition of duplicate for sets based on identity hash map, the ID set that you just saw earlier, because an identity hash map is intended, it's designed to distinguish every single element by its identity. So two elements aren't equal unless they are the same element for an identity hash map. And this is a useful data structure for certain things, like for eliminating cycles in serialization and that kind of thing, or detecting them. So it's not like it's not useful, but it certainly does not use equals in order to define what is a duplicate. And tree set and navigable set, these implementations of the sorted set interface, they use a comparison method for deciding when two things are equal. And so you saw in the little demonstration that we had there that if you added an uppercase A and a lowercase a to something that was sorted on string insensitive comparison, they're the same. So what's in red there doesn't look like it's the right thing for certain kinds of sets. So what actually is a duplicate is not in fact defined by the contract for set. It depends on the set implementation. Duplicates are pairs that satisfy what's called an equivalence relation. And the equivalence relation is very simply the relation that divides up all the possible elements in the universe of things that could go into the set into equivalence classes, and the set can only contain one element out of each equivalence class. So for a hash set, the equivalence relation is indeed E1 equals E2. For a set based on identity hash map, the equivalence relation puts every single element into a different equivalence class. And for sorted set implementations, it's a comparison method. Sorted set implementations, the tree set and navigable set and so on, same for the maps, can be constructed either out of elements that have a natural order, that is they know they can compare, one of those can compare itself with another one, which is the bottom line, E1 dot compare to E2, or they can be constructed with an external comparator that does that work for them, which is the top line, compare E1, E2. And in each case, either the comparable or the comparator or the comparable has got a comparison method which supplies the equivalence relation. So just to take a little bit of a side detour on this, you might think from this that from this idea of the string, the case-insensitive order, you might think that comparison methods are always going to lead to trouble, but that isn't the case at all. The specification of the sort of comparator and comparable and comparator, I think, says that the comparison method should be consistent with equals. And it says terrible things will happen to you if it isn't. I feel like it doesn't say what they are, but it does say you really shouldn't do this. Yeah. It doesn't even say you can't do it. It just says you shouldn't do it. It's really, really unhelpful.
There's a line in the specification which we intend to rewrite someday once we figure out what to rewrite it with. But it says something like, if you do this, the set will work perfectly. It's just that we'll behave strangely. Okay, thanks, guys. I think it was Josh Block.
It was Josh, yeah.
But what I showed at the demonstration at the beginning was examples of strange behavior, which is the whole point here. So
we're going to be a little bit more precise about exactly what that strange behavior is today. So if a comparison method is consistent with equals, then none of this arises. You follow this finger-wagging advice, the kind of vague but ominous warnings in the
Exactly.
in the documentation, and you will be all right. A comparison method is consistent with equals if it returns if E1 compare to E2 or compare E1 and E2 return 0 in exactly the same case that E1 is equal to E1 equals E2. And lots of comparable and comparator implementations are exactly like that. I mean, for example, strings are. The compare to method, the natural order of strings, is indeed consistent with the with equals, and so it is also for the integers, the numeric wrapper classes, and so on. And that's the normal state of affairs. But sometimes it's useful to have things that aren't. So string.compare to is consistent with equals. String.case-insensitive order is inconsistent with equals, which is where it gets interesting. And ordered sets having comparison methods consistent with equals are just like sets with equivalence relations of equals. We don't worry about them. So let's think a bit about what's actually happening here. I've talked about I've talked about duplicates. The real way of telling whether or not you have a duplicate in a set, or the way a set tells whether or not it's got duplicates, is that it uses the contains method. So it asks, typically a set, if you try to add something to a set, it'll say, do I already contain this object? And if I do contain it, I won't add it. If I don't contain it, then I will. The semantics of contains reflects the set's equivalence relation. For example, we just saw that when we set up, with the setup that we had there, we created a new tree set with a case-insensitive order. We added A and B to it, never mind the B, that's not important. We added a capital A to it, amongst other things. And then we asked, does it contain capital A? And it says yes. And we asked, does it contain lowercase a? And it says yes, because it's a case-insensitive order. So the way that the contains is implemented is it says if I compare this candidate element with the one with all those that are already in there, if I use the comparison method, will it return 0 in one of those cases? And the answer to that question is, of course, yes, it will do, because as far as case-insensitive order is concerned, lowercase a equals uppercase a. Are we okay? And what we saw was that as a result of that, tree set equals a new hash set that contains uppercase a and lowercase a. Never mind the b that was in tree set. So you might ask, well, like, how does that follow? That evaluates to true. Why does it do that? And the answer is, everything depends on the contains method. So let's have a look at the way that the tree set determines whether or not a set that is supplied to it is equal to it. Here's how it determines it. This is simplified and refactored, and so it would fit on a slide. But roughly speaking, this is what it looks like: an abstract set, which we've already met. So what abstract set method for equality does is it compares the two sets for size, and if they're the same size, which they were in this case, both of them had 2 elements, it then iterates over the argument, and for each element in the argument set, it says, do I contain that object? And of course, the hash set contained uppercase a and lowercase a, and the tree set says, yeah, I contain both of those, because my element a, uppercase a, is equal to both of those. Right? So, I mean, like that, is the algorithm wrong then? I mean, like, is that just a stupid way of doing it? I mean, possibly it is. I mean, I'm not going to say that I didn't write that. I didn't write this stuff.
Yeah.
But the point is, though, that even if it is wrong, that isn't the point. I mean, I've said no, it isn't. But actually, I mean, it's a reasonable algorithm. The problem is that equality between sets will always depend on the contains method. So equals between sets with different equivalence relations just isn't well defined, because which of the contains methods are you going to use? Now, if you've got different contains methods, then you're going to get different answers. And that's why the equals relation that you saw at the end, at the end of that little script, was anti-symmetric. Well,
No, it's asymmetric.
it just wasn't symmetric. It just
Yeah.
wasn't symmetric. So you ask the tree set, are you equal to the hash set? And it says, yeah, sure. And you ask the hash set, are you equal to the tree set? It says, no way. And that's always going to happen if you have two different contains relations. And this problem spreads out into everything that depends on the equivalence relation. So operations that connect two different sets are always going to go wrong if the two sets have different equivalence relations. So contains all, remove all, retain all, these connect sets, and they're not going to work properly. And collections.disjoint as well, the disjoint method of the collections class. And this is the behavior that those vague but ominous warnings in the documentation are designed to tell you about. Well, except they're not explicit. But this is what goes wrong. If you try and connect two sets with different equivalence relations, then you will get these behaviors that you don't expect and that you don't like either. So go ahead.
Yeah, I wanted to interject something here. So it's like, so is the algorithm wrong? It's like, well, you can consider alternatives, and it's not clear that the alternatives are any better. So one of I think the problem we're stating here is that we have sets. Java has different kinds of sets in the system, and they use different equivalence relation. What does equality mean in that? Well, in fact, it's ill-defined. So if you use equals on sets that have the same equivalence relation, it all works perfectly fine. The problem is when you mix them. Now, if the problem occurs when you mix them, maybe we should have used a different definition of equals. Maybe we should have said, oh, if sets use different equivalence relations, then they can never be equal to each other. But the original design decision was that it is always possible to compare sets of any implementation with any other. And so that's the road not taken. And one of the problems is, I think it's actually intractable to figure out whether two sets have the same equivalence relation. I mean, consider two tree sets with different comparators. They might actually implement the same equivalence relation, but you can't tell. So that, hypothetically, that would be nicer to say, two different things would never be equal, but in practice, you can't do that. So we have a situation here where set equality is more inclusive than it should be, but the consequences that expose this inconsistent behavior.
Right. So is this a really bad situation? Well, it isn't if you understand it and you know what to do about it. These sets, these things like identity, the identity, let's call it identity hash set, and certainly the sorted set implementations are very useful. They're useful specifically for specific algorithms and implementation of specific data structures. So it's entirely reasonable. I mentioned serialization and cycle detection. I'm pretty sure that's what.
Yeah.
That's a kind of classic thing that identity hash map is used for. But you may well have found plenty of uses for sorted set implementations in your work. And I certainly think that the navigable set in particular is a really good data structure. So there's no reason not to have these things. But actually collections have different purposes. There's the two broad purposes. One of them is this idea of data structure implementation, but the other one is, from a kind of a higher level software engineering point of view, they're useful for data interchange between different software components. If you want to do that, if you want to actually be able to pass between kind of widely separated software components, maybe written by different people, part of different systems, you want to have strong universal abstractions. You want to be able to depend on conventions that will allow you to process the data that you get from one part of the system confidently. You understand the basis on which it's been constructed when you're processing it in another part of the system. So and the problem here is if you get a set of elements from another part of the system, you don't know, and you can't tell what the equivalence relation of that set is. I mean, in principle, it could be you could have been the return value from the method that you called was a set, and it could be a sorted set, or inconsistent with equals, with a comparison method inconsistent with equals, or it could be a hash set, and you don't know. So, in terms of good practice for software engineering, a sensible thing to do is to go along with the set contract. The set contract says you can safely assume equals. Well, you can't safely assume it, but a good way of constructing large software systems would be to say, if we've got one of these sets that has an equivalence relation that is incompatible with equals, then probably the best thing to do is to keep it to yourself. I mean, it belongs in a class. It's doing useful stuff, but you can find it if you're going to start passing around sets or maps to unrelated parts of the system. The best assumption to make is that the set that you're passing around has an equivalence relation which does in fact conform with the equals, does in fact conform with the contract, that has an equivalence relation, in other words, that is compatible with equals, consistent with equals. So that's it. That's, I think, what I want to say about that. The conclusion is there's nothing wrong with having sets that have equivalence relations other than equals. They're perfectly fine, but they don't mix. They don't mix with one another if they have different equivalence relations, and they certainly don't mix with hash set, which is where the problems usually come. So keep them encapsulated. For data interchange, assume that an unknown implementation of a set or map is using equals as its equivalence relation, and obviously, when you're returning a vanilla set or map, you also want to use that, abide by that convention as well. So what about the set contract, which says explicitly that the equivalence relation for a set should be equals or should be consistent with equals? Well, my view is it's wrong. I mean, this is controversial, I think,
yeah.
but I just think it's too restrictive. I mean, we've got these perfectly legitimate sets. They do, in fact, behave quite well. If they don't obey the contract, I think the contract's wrong. I think the contract is too restrictive.
Yeah, I think this is mostly a specification issue because this one part of the specification says it uses equals, and then in the same specification, that is Java SE, it allows you to combine these things that violate this other part of the specification. So I think we just have to fix the specification so that it allows this, at the same time providing the right guidance to say, okay, there are these other things that use a different equivalence relation, keep them encapsulated because that's the best thing, and then the primary one, but not the required one, is equals.
Yeah.
Okay?
Right.
All right. I think we should move on in the interest of time.
Oh, right, Did I take too long?
No, but if we... Sorry, I was thinking you were going to ask for questions, and I probably don't. Right, okay. I think we don't have time to take questions.
Okay, we'll take questions at the end if we get time to take questions at the end. Right. Okay. So the other design controversy that we get quite a lot in the Java collections framework, and this comes up over and over again, and has done for the last 25, getting on 30 years, 25 years, has been immutable collection types. Why don't we have immutable collection types? And you see this coming up again and again, and quite often people say, well, it's really simple. All you have to do is just extract out the mutator methods into an immutable type. What's the problem? In fact, Josh did in fact foresee this in the original collections framework design FAQ. His argument was that distinguishing, and you can still see this, it's in the documentation of the of Java util, isn't it? Right. Distinguishing modifiable or immutable unmodifiable or immutable types leads to an explosion in the size of the type hierarchy. And he goes into this in a bit of detail. And he cites what I've called a mixed experience, but it's basically an unhappy experience from an actual framework which actually tried this out. And it wasn't, and this actual framework was developed by Doug Lee, so it was like, that means that it wasn't somebody stupid trying to do it, but it didn't work very well. and in fact got this explosion in the number of types. So, but the argument keeps on getting rehashed. So we thought in this section, we thought we'd look and see what's the alternative to what we have at the moment, which is, of course, optional operations and unsupported operation exception. Why do we have the optional operations arise mainly because of collection views? Well, actually, they arise partly because we actually want to have unmodifiable collections, like in the first line. I mean, this man has actually introduced a lot more occurrences of optional operations with the Java 9 collections, because the unmodifiable collections that were introduced there will throw unsupported operation exception on all mutation operations. And of course, they were deliberately introduced at the start of the Java collections framework with collections.unmodifiable list, unmodifiable set, unmodifiable map, and so on. But they also occur because of collection views. So arrays.asList, for example, gives you a view on an array which allows you to use some set methods, some list methods. Sorry. So you can, for example, you can use list.contains and you can use list.set. And so on. But you can't use list.add, or at least you can't use list.add without an index, because the backing structure is an array, and that you can't remove elements from such a list. Again, because the backing structure is an array, and you can't do something to an array that you can't do to an array, and arrays in Java are fixed size. Similarly, the key sets and maps, you can remove a key from a key set of a map because the underlying operation will remove both the key and the corresponding value. But you can't add a key to the key set of a map because, like, what would the value be? So these optional operations are kind of really baked into the collections framework. And the collections that expose these optional operations have the same type as mutable collections. So they expose the mutable operations. We don't have a special type for the return value from arrays.asList, which would be something like fixed length list, or the return type from calling the key set on a map, which would be unaddable. Unaddable set, but unaddable but removable set, something like that. So we don't have any of those. We just got set, list, and map. So these things expose the mutation operations that in some cases they can't actually they can't implement, and they called unsupported operation exception. And people complain that when they're given one of these things, a set or a list or a map, how do they know what they can do with it? So let's suppose that we were going to try to meet the objections that these people have, and we were going to actually try to define immutable collection types. So we're just going to play around with this idea for a couple of minutes of just seeing what would happen if we tried to do this thing, which I've seen quite often referred to as really easy, which is let's just extract the mutation operations and make them into the accessor operations, and an immutable interface would contain only accessors, only getters, and read operations, in a word. And then we could subclass that. Well, we'd have to subclass it because if you think about it, this immutable list, so-called immutable list, it's just a naming experiment. This immutable list, which only has size and get and an iterator presumably without a remove method, and so on. That's got fewer operations on it than mutable list, which adds to that. The subclass there adds the set method and add methods and so forth. So that kind of looks in terms of it looks for a moment as though in terms of subclassing, and there's a classic thing about how inheritance adds on new methods in the subclass, that kind of looks like it makes sense. It certainly doesn't. It's certainly not obvious that you could have it any other way around. But the problem with it, the problem with this is that if you think about it, the other aspect of inheritance is the is-a thing. You know, that anything that inherits from a supertype is a kind of that type. So array list, for example, which is obviously a kind of mutable list, also transitively turns out to be a kind of immutable list. That doesn't make any sense at all. In fact, every mutable type, everything that inherits from mutable lists is going to be a kind of immutable list as well. So it's sort of a neat-looking type distinction, but it doesn't really make very much sense. So at the very least, it means that immutable is the wrong name for an interface that just lacks mutators. I mean, it's clearly not enough. So maybe that interface should be called something like read-only list. That seems like a better name. It certainly describes the interface better because, I mean, clearly the interface, the immutable list interface, doesn't do anything about being immutable. It just lacks mutators. It's much more precise to call it a read-only list because that's at least what it is. But you still have exactly the same problem with mutable collections. They still don't belong in it. And you may have had the idea that, additionally to that, you may have had the idea you were going to get some kind of security. Supposing you got, for example, supposing you want to hand out. You're an object. You've got your data. You want to make sure your data is secure in the kind of way that we described earlier on, but not doing what we did there, but just handing out a reference to a read-only list. Supposing that was a way of handling, an alternative way of handling the problem that we talked about in the encapsulation section of this talk. So you would pass out. You might have your internal data structure might be an array list, but your getter would return a read-only list. And you think, okay, well at least that's reasonably safe. I'm handing out a reference to a type that can't be mutated because it's got no mutator methods on it. But your client may not actually have the same view. Your client may well say, hey, you know what I can do? See the second line from the bottom? I'll just cast it back to being an array list.
You would never do that now, would you, Maurice? Okay, so how many people in the room would never admit to doing something like this? But this is one of these things where it's like people, I mean, rightly have reactions to this. And so I think the question is, so I think that a lot of people who would say, you know, this is bad code. Don't downcast like this. But code like this occurs in the real world. If you have a large system and somebody's trying to get their job done, this might be the fastest way to get it done, and everybody's under pressure to deliver their features. And so if you happen to notice, oh, that actually is an array list, I'll just take advantage of that, and I need to modify it, so I'm going to go ahead and modify it. And so, so code like this does happen. And so if you're a library author or maintainer, then sometimes it's wise to take extra steps to protect yourself against this sort of thing so that you can make modifications to your code in the future that don't break people. And you prevent them from actually in the runtime, preventing them from doing things like this.
Okay, so you're not going to get security out of changing the type in this kind of way. So naming experiment 3 is let's actually give this thing the name that it really deserves. We'll call it readable list, right? So that top level interface is now accurately described by that name. I mean, it is indeed. I mean, if it's got accessor methods on it, they can read it. Then it clearly is a readable list. So and that also does describe the mutable implementations as well. So we aren't actually we're not kind of lying about it. An array list clearly is a readable list as well as being a mutable list. So this does express the design intent. It implies if you hand out one of these things, this list is provided for reading. So that's good. But it still doesn't provide encapsulation. So, like, it's not really what people expect that they're going to get when they talk about immutable types, because what people really want, I think what they want, I mean, it's not entirely clear, but it seems like the dissatisfaction is with the fact that you don't get any security of immutability. So maybe the whole approach is wrong. I mean, I don't think maybe the whole approach is wrong. The whole approach is wrong, actually. So, you ask these questions in order to even to evoke the answer. Yes, the whole approach is wrong. You can't get there from here. The type hierarchy can't provide immutability, particularly in the presence of subtyping, because of this downcasting thing. We're just starting from the wrong angle. Instead of thinking about what we wanted from the type system, we decided that what we were going to do was like get a nice type and a neat type system that looks like it fits the kind of model of what object-oriented inheritance should look like. If we instead start from what we want, from the semantics of the different kinds of collections, we're going to almost certainly we're going to arrive at a different and probably more sensible conclusion. So I just want to say a quick word about unmodifiability versus immutability. I've given entire talks on this, so this will be, but I won't here. But I will try to describe very briefly. Almost all the time, we're talking about unmodifiability in the Java collections framework, and there's a reason for this. Unmodifiability in the case of a list means that the elements of the list can't be changed. But supposing that the elements, each element of the list is like an object that contains references, and those references can be changed, then unmodifiability doesn't say anything about that. It just says that the contents of the collection itself can't be changed. Sometimes people call this shallow immutability. So you may have come across that phrase. Something that's in the way that we're talking about it, something that's immutable or really can't be changed. The whole object graph cannot be observed to change at all. So it's like not only the elements in the collection, but the elements, the objects that they point to, and the objects that they point to, and so on, right through the whole object graph can't be changed. And that's genuine immutability. And that has some really useful properties in terms, for example, of thread safety. But it's quite difficult to achieve it's quite difficult to achieve in Java. It's possible to do it, but that's a subject for another talk, and I don't want to go into that in a lot of detail. I've been told not to go into it in a lot of detail, even though I have given talks on it. You don't want to hear those talks now. But I just want to say that
talk is hereby included by reference.
Yeah, included by reference, absolutely. But I just want to say that unmodifiability is what we're talking about here, and that's the kind of, it's much easier to achieve, and it's generally speaking what the language that we're dealing in. So what do we want from unmodifiability? Well, we want to allow for three possibilities. I mean, the first two are kind of obvious. I mean, thinking about the scenario that we talked about in the first part of this talk about encapsulation, you think about the ownership of data structures. One possibility is that we might want something that everyone can modify. So, like, we're not concerned about the safety of this thing in terms of its contents. We might want something that nobody can modify at all, and once it's been created, really is unmodifiable forever. And those two things are actually reflected in ArrayList for the first one, and the Java 9 collections, the unmodifiable collections. In the second case. And the third case is something in between. So the third case is, if you think again about what we were talking about in part one, the owner of a collection might want to be able to modify it, but doesn't want anybody else to be able to. So, or wants to be able to control who else can modify it. So if you put that in a wrapper, then collections.unmodifiable list means that you hand out such a thing. It means that whoever you've handed it to can't modify it. But you can keep the reference to the wrapped collection. So if we think about how we could represent these different possibilities in terms of list type, in terms of list types, because we're talking about list here, subtypes of list could represent 2 and 3. And it already does represent 1, obviously. But we would still need optional methods. And with optional methods, obviously, comes unsupported operation exception. And we would have to prevent subclassing. So nowadays, we have sealed classes and interfaces for that. And in a moment, I'll talk about Guava, which was designed before the days of sealed interfaces, and so had to use classes to make them final to prevent subclassing, because subclassing can always lead to the problem that I showed you earlier on. So that's what you could do in Java. Other frameworks have tried to do different things. So the Eclipse collections, for example, they took a different approach, and they've got parallel hierarchies for mutable and immutable collections, and they are actually pretty parallel. This is an interesting approach, and I'm not going to criticize it in a negative way here. I'm going to observe some of the consequences. I mean, some of the consequences are that you do get designer intent is clearly expressed by the hierarchy on the right-hand side. Security is a different matter, and where am I going? I'm going backwards. I didn't want to do that.
Here, I'll find it. Why don't you?
Yeah, it's all right. What did I do? Right, I've gone a long way back. Thank you.
Oh, there we are.
Sorry.
That one. Okay.
You do get the explosion of types that the design FAQ refers to. It's actually in spades, sort of thousands of types, literally, in the Eclipse framework. And there's also the problem of converting between the two different hierarchies. So it's an interesting solution, but it's different from the choice that was made for the Java Collections framework, which was specifically designed, and a very important aspect of the design of it was, this is for people that are not going to spend a huge amount of time learning the framework. It's got a relatively very small number of interfaces, and of course it does date to before the days of IDEs, which I think would probably make something like Eclipse collections very difficult to use if you couldn't discover the different classes there are using an IDE. So that's one approach. A second approach is Guava, and as I said, Guava actually uses classes. They specifically says, don't look on these as implementations. They're design. They represent design, but we couldn't use interfaces because of the possibility of opening implementations to the addition of new methods. So for that reason, they're final classes. Or Immutable list is final class.
Yeah. Well, actually, they're private classes inside.
Oh, right.
Sorry, they're public classes that have private constructors, so they cannot be subclassed publicly. Right. And so the Guava implementations are in fact all immutable, and so this is what gives them the advantage here. If you're using Guava and you have an immutable list, you have high assurance that it is immutable. Okay, so that's good. But also note that it extends collection and list, which means that they inherit all of the methods, all the mutator methods, and so they have to throw unsupported operation exception. So there's this trade-off here, which is Guava went the route of providing immutable types because they want that documented in their code. So if you're using an immutable list, you know, oh, okay, so I know this list is not going to change, but they decided not to solve the optional methods problem.
And you still get the proliferation of classes, not to the same extent, but you get. But there's still a lot more of them, as you can see from the diagram here. Okay, alternative approaches 3. Kotlin actually takes an approach similar to the one that we talked about at the start there. So they have a collection which exposes only accessor methods, and then it's subclassed by subtypes by an interface which is immutable. And again, you've got the same thing. There's the same approaches mirrored for list and set and map and so on. So there's considerable interface proliferation here as well. I mean, just out of interest, there's a experimental. Is it?
Well, before
Go on.
yeah, it is. Well, yeah. Before we move on to that, I think this is fine. I think Kotlin's reaction to the problem of Java's optional methods is to do this, and so they sidestepped the notion of immutable or readable or whatever, and they just said, okay, let's make the top one collection, and then the extension adds the mutator methods, and that actually makes a lot of sense. But it's also a little bit dangerous because I also hear from people who use a Kotlin collection and they get lulled into thinking that it's actually immutable when it's not. And so the name is pretty significant here. And so the name is very, very general, and it's trying not to give you any semantics, but people still assume, since there are no mutator methods on this interface, they assume that it's immutable, and that's decidedly not true.
Okay, and the last thing to observe, just in passing, is something that we've not talked about here at all, but the possibility that you might have an extension to Kotlin, the Kotlin X classes, include persistent collections, and persistent collections are some kind of how would you describe the?
Yeah, I think at some point we should have a much longer talk about persistent collections. But the idea of a persistent collection is that they expose things that look like mutator methods, but what they do is instead they actually produce a new edition of the collection with the modifications included, but leave the old edition of the collection in place. And so it really is immutable, because if you have a pointer to such a collection, it will never change. But if somebody says, oh, add an element to it, they get a new collection that is the old collection with this element added.
It's kind of the best of both worlds, but it's also
there are a bunch of dynamics about it, but there's a considerable amount of complexity, but also a considerable amount of value.
Right. Okay, so conclusion. The conclusion should start from saying, what would we like immutable types to give us, rather than just saying, well, we want them, which is the usual approach. And the answer is, well, they could convey programmer intent, and they could provide security, allow objects to distribute references to their state, confident that they weren't going to get changed subsequently. And they could allow objects to incorporate input data into their state with confidence that that won't be changed subsequently. And you might notice that that is actually exactly what we were talking about in part one of this talk. That's exactly what the conventions that we talked about there. They're not enforced by anything in the language or in the libraries, but as conventions, they will give you exactly that. So the idea of adding a new type hierarchy, which would achieve only what can be achieved by good practice and applying those conventions, seems like it would be a huge amount of work if it didn't add anything else. So one option would be, like, supposing a new type hierarchy did add persistent collections, for example, then it might be worth all of that work. But it doesn't look like there would be enough value added simply by providing immutable types to justify the huge extra complexity and the massive proliferation of types that you would get.
Or I would say immutable types layered over the existing collection framework.
Right. Okay, that's it.
All right, I think we better move on. I'm going to have to
really
click through these.
Time,
Clyde.
Okay, right. Okay.
Okay, so part C, item 1. So the next 20 minutes or so, I'm going to talk about some ideas for the future. We have no future plans and stuff, but this is an issue that comes up from time to time. Some people say, well, what if I want to add more than 2 billion elements to a collection? So when Java first came out and the collections framework was introduced in 1998 or so, 2 billion, okay, so first of all, there's 32 bits, which is the size of an int, but int is signed, so the highest positive number is really 2 to the 31st, and so it's really the 31-bit barrier, and that seemed ridiculous. It seemed like a ridiculous amount of memory to have back in the days, and so 25 years later, we're not quite bumping into the edges of it, but it seems more feasible to say, what would happen if you tried to add billions of elements to a collection? Or more importantly, what would you want to do with such a collection? So anyway, int is really laced throughout the APIs. Int appears in a bunch of places. but fundamentally, it's also in the language. And so if you create an array, arrays are indexed by int, and the maximum array size is integer.max value, which is a little over 2 billion. So if you want to have bigger arrays, that's another effort, but it's not likely to happen anytime soon. So I think we have to live with that limitation for a while, and that also reflects. I mean, it has impact on how you would implement collections because collections use arrays. Hash code is also an int. And so if you look at, so hash code is not a cryptographic hash, but if you look at any cryptographic hashes, they have hundreds of bits nowadays, and hash code returns an int. It's only 32 bits. So if you have many objects, they all have to be compressed down into a 32-bit space, and that is actually kind of a limitation. So anyway, so int appears in a bunch of different places. Okay, now size is one particular place where int appears. So what happens if you take a collection and add, well, some collections simply do not accommodate more than 2 billion elements. But in fact, some do, and there's this stipulation in the specification that says, if this collection contains more than integer.max value elements, then it returns integer.max value, which is a weird thing because most of the collections don't actually follow that. Concurrent hash map does, but several others don't. They actually return a negative number from size, which is terrible. But the problem is this is also weird because suppose you have something a collection that contains 3 billion elements, then you add a new element to it, and then you check the size. Well, the size is the same as it was before, but the size is actually different. So now size is lying to you. So this isn't very good. So concurrent hash map has a long size method that returns a long, which gives you the real size. And then there are other problems, like if you have more than 2 to the 31st elements, you call a two-array method. Well, that will fail because you simply cannot have an array that big. So that's another problem. And then list and list iterator, I think, are the worst because int appears in a whole bunch of those different APIs, and a list iterator allows you to index through a list, but it also allows you it keeps track of its current position. So if you have a list, heaven forbid, if you have a linked list with more than 2 billion elements, and you manage to get a list, actually you can start the list iterator at the end. Okay, great. So then you ask the list iterator, what index are you at right now? It can return an int. The only thing it can do is return an int. And so so there's a problem there. We wouldn't know what to do with that. So one approach might be, just convert all the ints to longs in the APIs. And you can't do that for compatibility reasons, but what you could do is add a bunch of methods alongside of the existing ones where a long is used instead of int. And that might actually work. You'd get a bunch of clutter and stuff in the API, but one of the problems then is what I was just saying a moment ago. All the int methods, all the int-based methods are still there. And so what does int do in the presence of a collection that has more than 2 to the 31st elements? And so that's kind of an open issue. But maybe you can hand wave around it. Like with the size method, you could say, all right, invariants start to break, and there's a way of asking a collection whether it's in this state where only the long methods work. So that's a possibility. Okay, so I think maybe if we wrestle the spec hard enough, we might be able to make some progress. Now let's look at implementations. All right, so suppose you had an array list and you wanted to add more than 2 to the 31st elements. Well, you can't because array list stores its elements in a single array. So that's basically a non-starter. Now, you actually can add more than 2 to the 31st elements to a linked list. And there are a variety of reasons why you do not want to use linked list in practice, but you can actually do this. And in fact, I have done so. We actually have a machine that has a large enough memory that you can have a heap large enough to accommodate a linked list with more than 2 billion elements. But one of the things about these linked data structures, not including linked list, but not limited to linked list, is that there is one Java object created per element in the collection. And Java objects are kind of expensive because you have an object header and you have to have space for the fields. And so a linked list node occupies 40 bytes. And so if you put 2 billion elements into a linked list, already you're using 80 gigabytes. And you actually haven't stored anything yet, right? That's exclusive of the actual elements you're trying to store. So the overhead is pretty high. But then the other thing is, what do you do with lists? Well, you could do something like index of. Well, that means a linear search. Yeah, you kind of don't want to search 2 billion elements using linear search. Okay, so hashing seems more promising because you don't have those issues about linear searching, and you can have order constant operations on it, which is good. But you run into some other interesting limitations. So hashmap and concurrent hashmap have an internal table which contains the buckets, and each bucket is a linked list, which is okay because those are generally small. But that internal table must be a power of 2. And so the largest power of 2 that is expressible in an int, and therefore is the largest array that is the size of power of 2, is only 2 to the 30th. So you can't, because 2 to the 31st is larger than integer.max value.
But only by 1.
Only by 1, but that's a pretty significant 1. So anyway, so basically that's only about 1 billion. Now let's say you're adding billions and billions of elements to a hash map. What's going to happen is that table can't be increased, and so the linked lists in each bucket start to build up. And that's okay. They're only going to be a few long. So if you have a good hash function, it's going to find you the bucket, and then you're only going to have to search a handful of elements. And you can actually pretty much store a few billion elements that way. But then what's interesting is, since you can't grow the table any larger, the linked lists get longer and longer and longer. And so what hashmap and concurrent hashmap do is, when the linked lists get long enough, they convert them into trees. And so if your elements are comparable, then you get a log. You can search the bucket in a log n algorithm. And so those can actually get quite a bit longer. Each bucket can get quite a bit larger without too much of a problem. The problem, though, is that once again, we have 1 node per element stored in the collection. And a tree node is actually 96 bytes because there's a bunch of things in it. It has a bunch of fields and the object header. And so if you wanted to store 8 billion elements, which is when the tree nodes start to come in, then the overhead of keeping track of all of those is 768 gigabytes. And again, that's not even including the size of the elements you're storing. So you could do it, but it's not practical. And so that leads us to this question here, which is, what are you trying to do with a collection with this many elements? List, you probably don't want to work. You're not going to search down to the middle of the list and insert something in the middle if you have 1 billion elements in your list. It kind of doesn't make sense. So probably something like a hash map, something hashed, or something where you can operate on different parts of the elements, collections. You can operate on elements independent of other elements. But then you have the per element overhead. So what we need is something in the middle. We want to store large quantities. If we want to store large quantities of elements, we want to use arrays, but we have to use multiple arrays. And so probably storing multiple arrays in some kind of tree structure is a likely approach to doing this. But the question is, we don't want to go out and build something like this speculatively. The question is, what are you going to do with this stuff? Are you going to add things sequentially? Or are you going to do random access? Are you going to do searching? The things need to be sorted. So there's a whole bunch of questions about what the use case for this is, which we don't know enough about yet. And only when we have good use cases would we actually start to build something like this. Now, there is already some possibilities for storing and operating on large amounts of data in the JVM, but it actually doesn't use collections. And so most things that use gigabytes and gigabytes of stuff don't use objects to do it. They're usually manipulating large amounts of data, which is in the form of primitives or matrices or something like that. And so Panama the Panama project, which delivered into a fairly recent JDK release, introduces this concept of a memory segment, which is essentially an array that is indexed by long, so you can get up to 2 to the 63 elements, and well, basically an array of bytes, and it's stored off heap. And so, so if you wanted to access that off-heap memory, you can use var handles, or Panama has some higher-level constructs called layouts that let you say, okay, I want something like a struct at this position in the memory segment. So people are starting to make good use of that. If you're operating on gigabytes and gigabytes of data, probably the thing to do is to look at that first, because you're probably manipulating data. If you want to manipulate billions of objects, then we don't really have a good solution for that in the collections framework yet. But also, I want to hear about use cases that people might have for storing billions of objects in a collection. It's kind of an obvious thing to say, oh, we should just change the ints to longs, but I want to hear about use cases before we dive into the implementation on that. Okay, so that's a quick tour of the 32-bit issue, and then I'm going to want to move on quickly to Valhalla and then wrap up. Okay, I'll just want to say at the outset, there is a Valhalla talk later in the conference where you get all the latest stuff on this. So I'm going to have to run through this really quick, and if I'm going to assume that you know a lot about Valhalla, and if you don't, go to the subsequent talk, which I will refer to. Okay. All right, but basically what Valhalla does is it kind of heals the primitive object divide, right? We have primitives, which are just values and can be copied around freely, stored in registers and stuff. And we have objects, which must be stored on the heap. And if you want to create a new object, if you want to create a higher level construct, then you're forced to move things onto the heap, which has a bunch of issues. The biggest one is identity. But also there are problems like, pressure on the garbage collector, and it precludes a bunch of optimizations. So if you write, Valhalla provides what are called value classes, and so a value is it's like an immutable class that has a bunch of stipulations around it, but the biggest thing is it no longer has an identity. And so you never, there's this weird thing where you can say you have an integer object, and you can say this integer object is different from this integer object. And that's a very weird thing. And so in if you have a value class, and you don't do that with ints, like the int3, you never say this int3 is different from this int3, because they're just values. And so the idea of Valhalla is that you can write a class that represents a value, and you don't get to ask whether you're talking about this instance of it or that instance of it. It's not part of the model. Now, the biggest issue that the Valhalla team has been wrestling with over the past several years is nullability. And there's this idea of, it's like, okay, if you create new objects, everything in Java today is nullable. You can have a reference to an object, or that can be null. And so what does it mean if you have a value object that's null? Does it mean that all its fields are 0? Because it might not be on the heap, so you might not have a null pointer to it. So maybe its values are zeros and stuff. So anyway, the team is converging on a solution to this, having to do with strict initialization, which you will hear more about from Brian Getz later on. But what this enables you to do is to say, okay, I'm going to create a value type, and I'm going to make sure that when it's initialized, it's every field value is well defined. That means I can create an array of them, and the value objects will be flattened into the array. And so flattening is the big win from Valhalla. So I'm going to have to skip over this a little bit here, but I think here. So I was just talking about hash maps. So here's a diagram of what the hash map looks like. So the array on the left is the table, and if you follow the chains, each it's like a linked list inside each bucket, and if you follow that around, they actually traverse randomly through memory. And so there are a bunch of problems with this, which is, one is that every every one of those blue objects is on the heap, and so it has a header. They're scattered all across the heap, which means that if you want to search a hash map, you do a lot of cache misses and so forth. And so, this works well for fast access, but there are fundamental limitations here in what we can do with this. Okay, and so suppose we could take each of these. So the blue objects are the hash map nodes I was talking about before that take 40 bytes each. Actually, on the next slide, I say 32 bytes, but oh, that's right. Linked list nodes are 40 bytes. Okay, so I'm just going to have to switch to this one here. All right, so the hash map technique I showed previously was called separate chaining. So if you have multiple elements that hash to the same bucket, they get chained into the same bucket. And the chaining is is separate, which means it's stored outside the table itself. Now there's an alternative organization. This is basic data structure stuff, but there's an alternative organization that's called open addressing, which is you actually store all the values in the table itself. And you can't really do this in Java very effectively because in Java today, because every object is a reference to something on the heap. And so the idea of Valhalla flattening is that you can actually store values, which is like a class with multiple fields, inside an array without any indirection. And so you can take those same objects and store them in a single array. And so I think this kind of thinking is the biggest advantage that Valhalla gives us when we're talking about collections, is this flattening notion. So there are a bunch of things you can do, you need to do in order to achieve that, but the team is working on them, and we think we'll get there fairly quickly. Well, I don't know about quickly. Compared to the last 12 years, they've been working on it.
Right.
Okay, so one of the things about value objects is that they are immutable. But, sometimes we like to mutate our maps. So can you build a mutable map out of immutable objects? And the answer is yes. And so what you could do, suppose you have a table into which you've flattened these value objects, and you want to change the value of it. Okay, so what do? So you create a new entry. Okay, so entry is a value class, and you create a new entry, and you copy the key from the old entry and copy the hash code from the old entry, but then you provide a new value. So now you've created a new value, and then you store it into the same location in the table. So from a conventional Java standpoint, it's like, why are you doing this? Why don't you just mutate the entry itself? But since these are values and since they're immutable, then you have to replace the entire table entry. Now, here's where the JIT optimization comes into place. It says, so entry does not have an identity, and it does not need to be allocated on the heap. And so the JVM can say, okay, I have this entry in table sub I, and I create a new entry that contains the old entry key, the old entry hash, but simply replaces the value. And so the optimizer can work over that and say, oh, the only thing you are actually doing here is replacing the value slot in the table with the new value slot. And so this code that looks like it's doing memory in classic Java, it looks like it's doing memory allocation and doing some initialization and copying, basically gets turned into a one-word write. And that's the advantage that value objects give you, because since there's no identity here, and since the just the properties of value objects are so good, the JIT compiler has a lot of knowledge about what optimizations it can make. And so this is one of the things. Now, this is one of the things that it can do. In addition, one of the things the Valhalla team is considering is that we expect this kind of code to be done quite frequently. And so you might want to create a new value object that is mostly a copy of some old value object with just a couple slots replaced. And so they're toying with the idea of what are called withers, which is a new programming language construct that basically says, give me a new value that's the same as the old one, except with this replacing that. And so I'm not even going to show the syntax for that because it's changed around a lot and it's all speculative anyway. But I think that's something that would make, instead of what we have here is sort of a verbose way to do something, is we had to create a local variable and kind of copy things over manually, and then which is kind of verbose because we are hoping that the JIT just optimizes that all away. Okay, so that's one of the big promises of Valhalla. Generic specialization is something that's gonna take longer after the initial value class flattening stuff. But the idea there is that you should be able to have a list of value type. And so some of you may be familiar with collections frameworks out there that have like list of int. And so, but you can't have a list of int using the generic type system because in today's Java, you can only generify over reference types. And so Valhalla, we hope, will eventually get to the point of being able to specialize not only over reference types, but also over value types. Okay, so anyway, so really not enough time to cover all the stuff that's going on in Valhalla. Brian Getz is giving a talk on this. I highly recommend doing this. This is Thursday, I believe. Last time I looked at the schedule, this was Thursday at 11:50. And also there's a JVMLS talk that he gave in the summer, which is probably an earlier version of the talk, and that's on YouTube. Okay, so we are at the end.
1 minute and 45 seconds
Yeah,
out.
well, but there's something we have to say. I'll let you do the honors.
No,
okay.
you do it.
Buy his book.
Well, it's our book, I think, by now.
Okay. So I think we'll be around for a little while for Q&A. We don't have any time in the session for Q&A, but here's how to reach us. We have email and websites for the unconferences. I'm on Mastodon these days, and so I'd be very happy if people do their interaction on Mastodon.
Right.
Okay.
Thank you very much for your attention.
Okay. Thank you.